Hello everyone, I'm Jim Fengdan from ICT Channel Academy Science and Bench Council. The many contributed to AIBench. We just list some company and some academic institute. More information can be available from their website. For the part, I will talk about the challenging. I think no one will doubt that AI is one of the most important modern computer workload. From IoT to supercomputing, from edge to data center, AI algorithms are widely used in different application scenarios. So I think different from traditional workload, such as desktop workload, web server, modern computer workload have different challenges. First challenge I think is how the fragmented application scenario is a marked departure from past. For example, we can find a whole variety of application scenario and modern scenarios. For example, for different application, we have machine perception, machine learning, natural language processing, knowledge implementation, reasoning, automated planning. We also have different AI model. So for AI, for example, for AI chip, I think there are several hundred different AI chip. So that's also why AI benchmarking are urgent. The second challenging for modern computer workload is isolated. I think real-world data set and workload, or even AI model, treated as first-class confidential issue. So they are isolated between academia and industry, or even among different providers. For example, for electronic commands provider, they use different AI model from social network. Okay. So microservice architecture are widely used in industry. They are distributed across different data centers. It often consists of diversity of various modules with very long and complex execution paths. Meanwhile, the tail latency is very important. So under this context, AI are widely used to augment into internet service or other service. So meanwhile, AI benchmark also raises very serious challenges. The first challenge is prohibitive cost. Because the learning dynamic, we have to run an entire training session. Someone may be feel confused why we have to run an entire training session. Because for many optimization, if we do not observe an entire training session, we won't know the optimization will, how about the optimization effect on the quality, the final model quality. Maybe it optimize the throughput, but it will hold the final model quality. So it's why we have to run entire training session. But it will take several weeks to run a complete training session on small scale system. Meanwhile, a simulator, our architecture community widely rely upon simulator. It will slow down times or even 100 times. This which is exactly the challenging. Meanwhile, so a second challenge is the conflicting requirement in different stages. For in the early stage, we need the benchmark be affordable because we cannot put many applications on to a new architecture, new system. At the late stage evaluation, we need to benchmark a comprehensive and representative because some perfect number using a few benchmark may be misleading. So the third challenge is sort of self-life. I think the AI model evolution change all the pace in the AI benchmark. Maybe we take 1 year to work through benchmark design, implementation, community adoption, and large-scale testing. But the AI model evolve very fast, changing very fast. They may outpace the AI benchmark. Synthetic benchmark like a DNN can traverse many network, but it cannot model learning dynamic. I think the learning dynamic are very important in deep learning. I will explain later. The third challenge is scalability challenging. For example, for most AI tasks, I think a problem scale is often fixed. For example, for HPC AI is scalable, but it cannot model the learning dynamic. Meanwhile, it also fails to consider the model quality. For example, for this picture is from HPC AI 500 ranking. For ImageNet, using ImageNet dataset and image classification methods, the recent result for recent state-of-the-art data, the most strong system only need several tens of seconds to finish an AI task. So it cannot stress test a large-scale system. So we need to consider how to tackle that scalability challenging. The fourth challenge is repeatability challenging. The benchmark mandates being repeatable, especially for system, for benchmarking large-scale system. While training deep learning is stochastic. For example, there are many factors of randomness. For example, model acceleration, data argument, data shuffle, dropout, something like that. This picture shows the run-to-run variation of AIBench training. For example, for 3D face recognition, the number of epoch to train a state-of-the-art quality, the variation is about 35%. I think it's very large. For example, the epoch to achieve target quality varies significantly on different random sets. For example, run image to text from AIBench training 4 times using different random sets. We can see the epoch to quality change very differently. So we want to talk about the related work. I think for AI benchmark, the first one is the fashion. It includes 8 workload, provide training and inference benchmark, but it does not use quality metric. Then DNMark provide 8 micro benchmark, but it cannot provide the component benchmark. Baidu provide a DeepBench. It provides AI basic operator containing GMM convolution, recurrent layer, and all reduce. It only has micro benchmark. DownBench is the first benchmark using time to accuracy as a metric. I think so-called end-to-end AI benchmarking. Then the TPD suite, it provides 8 workload from 6 domains. Our benchmark AIBench, the first paper appeared at Bench 2018. It proposes scenario benchmark. Scenario benchmark means it model critical paths of real-world application scenario. It includes 19 tasks, AI tasks, provide 19 workload. Meanwhile, it also provides subset. Meanwhile, another concurrent work is MLPerf. It provides 7 workload from 5 domains. HPC AI benchmarking, I think the first one is DownBench. DownBench provides image classification question answer, it perform large-scale testing. It's the first AI benchmark that uses AI time to accuracy as a metric. HPC AI 500 is from our group. It is the first paper. The first paper appeared at Bench 2018. It covers 3 representative applications of scientific deep learning. It also provides hierarchy benchmark methodology using valid flops as a metric. Deep 500 is another HPC benchmark. It is published at IPDBS 2019. It provides HPC AI benchmark framework, but it provides no concrete reference implementation. HPAI is proposed by Professor Jake Dangra. It's a micro benchmark based on AU decomposition. It's scalable but cannot reflect model quality. MLPOF is also currently also provide HPC benchmarking. Another one related was AI benchmark for edge computing. I think Edge AIBench is the first one AI benchmark about how to model AI scenario across an IoT edge in the data center. It provides 4 application scenario: ICU, patient monitoring, camera monitoring, smart home, automatic driving. It also integrated federated learning. AIBench is from UCC companion. It also provides speech recognition, image classification. Another Edge AI benchmark is from EMBC. Meanwhile, there are also IoT AI benchmarking. The first one is from ETH. It have provide AI benchmark, also provide AI benchmark ranking. It is reported many number. We also provide AIoT bench. It support Android and another IoT device. It provide several AI framework implementation, for example, TensorFlow, KV2. I give a very simple summary of related work. DownBench is the first benchmark that propose time to accuracy as the main metric. AIBench is the first benchmark that notes the necessity of modeling the creative path of a real-world application scenario. Paradigm from Harvard University is the first synthetic AI benchmark. The HPA AI is a micro benchmark that uses mixed precision AU decomposition to achieve outbound flaws performance. HPA AI is a micro benchmark, is scalable, but AU decomposition is not relevant to most of AI workload. Both Paradigm and HPA AI cannot model learning dynamic, also fail to consider the model quality. So in this section, we talk about AIBench methodology. Could you hear me?
Yes.
Okay, let's continue on. AIBench from International Open Benchmark Council is a non-profit international organization aimed to promote the standardization, benchmark evaluation, incubation, and promotion of PC, cheap AI, big data. The project homepage is part already from this website. Overall, it provides scenario benchmark. It models creative paths of real-world application scenario. Edge AIBench is an instance of AIBench scenario benchmark. It also provides AI training benchmark. As we include 19 AI workload, so for affordability, we also provide AIBench subset. For HPC system, because the benchmark cost is very heavy because you have to perform testing on very large scale system. So we also provide HPC AI 500 benchmark on the basis of AIBench subset. Meanwhile, we provide AIBench inference. I think different from MLPOF inference, for our AIBench inference include many different AI model. The reason is very simple, because for inference workload, the overhead is very small. So we can include a comprehensive workload. Meanwhile, we provide AIBench is a lightweight implementation of inference workload on mobile device. Meanwhile, we provide micro benchmark for architecture community. I think for for architecture community, the training benchmark are too heavy to run. So we provide the AIBench training and AIBench inference workload. We provide a hotspot function for architecture simulator. Meanwhile, we provide a synthetic AI benchmark because AI model changes very fast. So we cannot, currently we develop a new AI chip for AI workload, but someday maybe we provide a new AI model. They have used different hotspot function, different operator. So this situation is we also found that the current AI chip, for example, for AIBench workload, we run on TPU. TPU is a very good AI chip from Google, but we found that TPU cannot support running many AI models. So this situation is very important. So we provide a synthetic AI benchmark. We can model the future AI model. So this summary, we explain our methodology. First, we start the real world future application scenario. And we separate the real world application scenario. For many application domain, I think the AI-based application are not developed. So we also consider maybe we can propose some specification for future application scenario. Then we can model the critical path of real world application scenario as a permutation of AI or non-AI module. Someone maybe just say, oh, why do you include a non-AI module? Actually, in the United States, I think for many applications, they also include AI and non-AI part. Meanwhile, AIBench, Edge AIBench is dense of a scenario benchmark suite, modeling end-to-end performance across IoT, edge, in the data center. I think for this scenario, because we can, for the same requirement, if we distribute a different workload, different model on different layer of the system, for example, we can propose a different collaboration policy on different layer. So it will affect the overall system very significantly. So AIBench and AIBench training and AIBench inference cover 90 the preventive AI tasks. We will continue to update. As I mentioned earlier, the AIBench focus on methodology, framework, and a continuous improvement with state-of-the-art model to guarantee diversity and representativeness. Meanwhile, AIBench provided two subsets for the repeatable performance ranking subset and workload creation subset to improve affordability. Meanwhile, to evaluate a large-scale HPC system, HPC 500 derived from the AIBench training repeatable performance ranking subset. I emphasize the repeatable because for HPC system, if benchmark have very high readiness, it cannot accurately measure a system. So we must guarantee the subset chosen from full AI bench training workload, the chosen workload are repeatable. To evaluate various IoT and embedded device, AIBench is derived from AIBench inference. It provides a lightweight model on different lightweight framework. Meanwhile, AIBench micro provider intensively use the hotspot function provided from AIBench training inference for simulation-based architecture research. As a complementary to real-world benchmark, AIBench synthetic provides several synthetic benchmarks with scalable problem size while model learning dynamic. As I mentioned earlier, most AI model, its problem size are fixed. So we use synthetic benchmark to provide a scalable benchmark tool. Meanwhile, we model learning dynamic. So this is the AIBench methodology. Sorry, we have a little party. It will make noise. So the first question is the micro benchmark sufficient. AI workload need to consider both computation efficiency and model quality. Flops no longer the only metric. For example, mixed precision training significantly improve flops. However, it may deteriorate the model quality. For example, from this figure, we can see flops comparison with ResNet 550 model, the mixed precision optimization can significantly speed up the micro benchmark. But if we take a look at the performance of component benchmark like ResNet 15, we can see the optimization will decrease the target quality. Meanwhile, for example, for HPA AI, it just using a single kernel to model to reflect the benchmark, but it's not the case for AI benchmark because, for example, we provide 17 AI workload from AIBench. We found that some micro benchmark may occupy the leader percentage. There are many different diversity of micro benchmarks. So which one we should choose? Another question is component benchmark sufficient to evaluate the AI system. For example, we benchmark with single component named image to text is OCR. We can use some OCR model pruning optimization. It can shorten tail latency by 51%. Meanwhile, the accuracy loss is only 1%. Someone may say, oh, this is good result. But if we take a look at put the component of the last scenario, we consider the overall system performance. We can find, for example, image to text is a small part of this scenario benchmark. We can find we use a thin OCR model pruning. We can find tail length have no improvement because the image to text take a very small percentage of overall performance, while the accuracy loss is also kept the same, is 1%. So for the second case, we can conclude that the optimization does not work. So using component benchmark alone will lead to misleading conclusion. Meanwhile, we found the single component versus the electric application. For example, for electronic command search intelligence, the overall system tail latency deteriorated even 100 times compared to single component tail latency. For different component, the number is different. For example, so for the recommendation component, the number is 2.2 times, while for text clarification component, the number is large as 180. Meanwhile, we also need trade-off model accuracy versus quality of service. For example, for electronic command search intelligence, we replace ResNet 50 with ResNet 152. You have multi-layer for implication clarification. Model accuracy improvement is about 1.5%, but the latency deteriorated by 90.790. So benchmarking a single component cannot reflect the trade-off between model accuracy and QoS. We have to put the benchmark into a full application scenario. Meanwhile, someone may just ask, does the static model predict the overall system tail latency, so providing many component tail latency performance? The answer is no. with two different models, for example, simple queuing model, Soviet queuing network model, we found that we cannot model the zero replicate scenario. So we have to use zero scenario benchmark. So a scenario benchmark is a process of zero elastic application scenario. It captures the created path and the primary module is the population of a series of AI and non-AI components. This is a scenario benchmark. It counts search intelligence, including a query generated online module, offline module, data storing model. You can read the technical report from a project homepage. AIBench is an instance of a scenario benchmark suite. It modeling end-to-end performance across IoT edge in the data center. The project homepage is this one. We also have to have a paper. Currently, it provides 4 typical edge AI scenario. Autonomy vehicle, it focuses on latency sensitive, high accuracy in the mobile scenario. Another one is ICU patient monitor. It's latency sensitive. Also provides surveillance camera. It includes MNOS data, very large number data. It also provides smart home scenario. It includes heterogeneous device and data. This is basically the summary of the edge AI task. I think that Tian Hao will provide much more detail in the later talk. I just give a very short summary because time is also very limited. We have used 48 minutes. Another one is AI training. AI training consider conflicting benchmark requirements in different stages. For example, I just mentioned earlier. So we consider diverse behavior for workload curation, include micro-architecture level, such as flops, memory access pattern, compute pattern, I/O pattern. System level include iteration time cost, variation, convergence rate, for example, how many epochs to train or state out quality, number of host function. Also, we provide algorithm level, include model architecture and parameters. AIBench training include 19 workload. We have a part that is part paper. You can find more detail from that paper. For example, take econs as an example. We have image classification, object detection, spatial transform or translation, recommendation, learning to rank, speed recognition, image compress from different applications. We just provide this component benchmark. In this figure, we compare AIBench training versus the MPOW training within 0.7. Basically, we provide a balanced methodology, consider conflicting requirement. We provide 19 tasks and model. We provide different data set. We cover much wide space in terms of computation, complexity, optimizer category, loss function category, hotspot function, different convergence rate. So I think there are different requirements for example, for performance ranking, we have to consider that fairness, it must be repeatable. Also, the cost must be very low. Meanwhile, for workload correlation, the repeatable maybe are not very important. Because, for example, for GAN, workload there is repeatability is very low, but it is a very important workload. So we also have to consider workload correlation. So we use some class algorithm. We have finalized 2 subsets for different purposes. One is for repeatable performance ranking. Another one is for workload correlation. Tangfei will talk about more detail in the later. HPCI 500, I think, is based on AIBench training subset, because it's impossible for run 19 AI workload on large-scale HPCI systems. So we just based on AIBench training subset. Meanwhile, for HPC AI 500, we must consider the workload must be repeatable. So we remove the unrepeatable workload. Currently, we include two workloads for HPC AI 500. One is the image classification. Actually, is a de facto HPC AI benchmark. Many groups using this workload to evaluate large-scale systems. Meanwhile, also include object detection. We provide two problem domains. One is extremely weather analysis. It is use object detection algorithm. Another one is image classification. I'll talk about AIBench inference. I think for AI inference workload, comprehensive workload are not important because it will take a very short time. For example, several seconds to finish inference workload. So that the overhead is very low. We can include a much comprehensive workload as possible. So we include diversity with data type, AI mode, AI framework. We also consider diversity workload behavior from algorithm system architecture perspective. Currently, it includes 19 workload. For example, coverage diverse network architecture, CNN, ZNet, STN, GRU, attention, and something like that. We provide text processing, image processing, audio processing, video processing, and the 3D data processing. The last one is AIBench. AIBench actually is implementation on mobile device or IoT device. It is the purpose is to evaluate the end device. AIBench covers representative and diverse model and framework. It provides a heavyweight model, lightweight model. It also provides a different implementation on different framework on TensorFlow Lite, KV2, PyTorch mobile. AIBench can be used for comparison of different AI model, different AI framework. Also, ranking AI ability of different mobile device. Actually, the different AI model architecture are designed with very different philosophy. Is widely used in the architecture industry. So we need to consider different AI model. The last one is a micro benchmark. Micro benchmark is the purpose is to tackle the prohibitive cost challenge, especially for architecture community, because on simulator basically it's impossible to run a training workload on a simulator. Meanwhile, you have to be easily portable across different architecture. Micro benchmark are much easier. Meanwhile, we provide a basic AI operator and we use hotspot code function from both AIBench training and AIBench inference. This combination of AIBench micro benchmark from deep bench micro benchmark, we think we provide a much more operator or code function. Meanwhile, also provide different data input. For example, for metric, we provide dense metric, dense spare metrics with a different size. The last one is synthetic benchmark. Synthetic benchmark to tackle the short self-life and scalable challenging. So we provide as a representative building block from AIBench training. We also provide different deep size and input size, different stride and pattern size. We also we also train the generative model to convergence to reflect learning dynamic, which paradigm cannot reflect. So we give a very short conclusion. AIBench design and abstract real-world application scenario called data science, HPC, IoT, and edge into the scenario training, inference, micro, and synthetic benchmark. This is